Hello everyone. In this class, we will continue our discussion on probability and random processes. In the last class, we defined sample space, then event, independent random variables, first random variables, independent random variables, then cumulative distribution function, density function of a continuous random variable, then joint probability distribution and density functions, and we also defined independent random variables. Now, in this class we will start with functions of random variables. If you have a random variable and if you take a function of the random variable with real value, that is the function takes the value of the random variable and transforms it to another real number. So, if you have such a function, the function of the random variable is also of course random, because the random variable has some randomness and the function will also have some randomness. The value of the function will also be random. So, the function value will be also a random variable. And what about its cumulative distribution function and density function? We would like to characterize that in terms of the function and the original random variable. So, let us do that. If we have a random variable x, and so we are discussing function of random variables x, and we consider another random variable which is a function of x. So, basically we have the sample space, then the original random variable x is a function of s into r, the value is a real number. Then we take another function g which converts it to another real number. So, then this function together, something here goes to here and then ultimately goes to here. So, this mapping from s to r itself, this mapping which is g and x together is also a mapping of s into r, and that is our random variable y. So, this random variable y also will have some probability distribution, and if it is a continuous random variable, it will have density function. So, let us consider an example. Y equal to a x plus b, and we take a greater than 0. If a is less than 0, the results are similar. We will not consider that here. So, what is the cumulative distribution function of y in terms of the cumulative distribution function of x? That is what we would like to find out. So, f y of y we want to find. So, this is by definition p probability that y is less than equal to small y, and that means probability that a x plus b is less than equal to small y. Now, what does this mean? This means that capital X is less than equal to b y minus b by a. So, this is the probability that capital X is less than equal to y minus b by a. But what is this? This is nothing but the cumulative distribution function of x at y minus b by a. So, we have expressed the cumulative distribution function of the new random variable y in terms of the cumulative distribution function of the original random variable x, what we wanted. Now, we also want to see the relation between their density functions, if the density function of both the random variables exist. So, let us find out. So, p y y density function, that is what we want to find out. This is d f y y by dy by definition. This is the definition. Now, this is nothing but d dy of this is equal to this. So, f x y minus b by a. Now, what is this? This is nothing but 1 by a, then the derivative of this with respect to this whole thing. So, that is nothing but p x y minus b by a. So, this is the relation between their density functions. Now, if we have some multiple random variables and we take their some multiple functions of those multiple random variables, then let us see what happens to their joint density functions and joint distribution functions. So, we have a set of random variables x1 to xn, and we will write them in short, just for notational simplicity, we will write them as a vector x. So, this is the vector of these random variables, and we take n number of functions of these vectors. So, the function take gi, the ith function takes all these values and then maps it to one real number. So, it is a function of all these random variables. So, gi of x1 to xn is a function of all these random variables, that is, it is a function of this random vector, and this function is also a random variable because it is a function of some random variables. So, this function is called the ith random variable yi. Then this can be also written as gi of the vector x, and there are n number of such functions g1 to gn. So, we get y1 to yn, and we denote those random variables, new random variables, by a vector y. So, this is our new random vector, which is a function of the old original random vector, and we assume that the set of functions is invertible, meaning by if we know y, the value of y, we can get back what is the value of x. So, in that case, if that happens, so this is basically we denote these functions together as a function vector g of x. So, this random vector is a function of the original random vector. So, that each component here actually is obtained by one function of that random vector, and this g is invertible, and we assume that the inverse is called f. So, x is f of y. So, there is an inverse function. Okay. Now, so this is basically, so every component, the first component of x will be x1 will be obtained by the first component of the function. There is one function f1 which gives us x1, f2 gives us x2, and fn gives us xn. So, these are the component functions. Now, given any such transformation of a vector, we can compute what is called the Jacobian of the transformation. So, what is the Jacobian? Jacobian is the determinant of the following matrix. Jacobian J is the determinant of del f1 del y1. Remember that this f1 is a function of this whole vector. So, this is f1 of y1, y2 and till yn. We are not writing those arguments, it is implied. So, del f2 by y2, del y1, del fn by del y1, del f1 by del y2, del f2 by del y2, del fn by del y2, del f1 by del yn, del f2 by del yn, del fn by del yn. This is the determinant of this matrix is it's called the Jacobian of this transformation f. Okay. Then one can show that if we know the density function of x, we can find the density function of the new vector, random vector y, in terms of it in the following way. P y, the density function of y at y1, y2, yn is Px. So, this is the vector y. You take the inverse, but you have to multiply by the Jacobian. So, this Jacobian is taken Jacobian of the inverse transform. See, this is the original transform is G. We take the inverse transformation and we take the Jacobian of that. So, this density evaluated at the function inverse, and then that has to be multiplied by the Jacobian of the inverse transform, and that quite conforms with what we did for the simple function y equal to ax plus b, because here we actually did that, computed the inverse x in terms of y, this, and then we multiplied by 1 by a. What is 1 by a? It is the Jacobian of the inverse transformation. Inverse transformation is x equal to y minus b by a, y minus b by a. The derivative of that is 1 by a. So, we have multiplied by 1 by a. Okay. So, example, a special case is this simple mapping where this vector is a matrix, invertible matrix times x. A has to be invertible because we need that the inverse transformation is inverse transformation exists. So, this A is invertible. Then P y y is P x A inverse y times 1 by determinant A. This is a very simple nice formula, and one can check that this is what happens, because what is the inverse transformation? X equal to A inverse y, and what is the Jacobian of that transformation? It will be just determinant of A inverse. So, determinant of A inverse is nothing but 1 by determinant of A. So, we do that. Okay. So, now there are some important quantities defined for some for a random variable, some average quantities. So, we will define those quantities. So, mean or expected value, it is called mean or expected value, or first moment of a random variable. Mx, the mean of x, is also denoted by Ex. It is basically minus infinity to infinity x Px dx. If it is a continuous random variable, then density function exists. So, we can compute the average value in this way. While taking the average, we cannot simply integrate, but we have to multiply by the density function. And if it is discrete random variable, we can take the summation over all the values and their probabilities, product of the value and the probability. Similarly, nth moment is defined as simply expected value of x power n. So, this will be simply x power n instead of x here, and then same as before this, or if it is discrete random variable, we will have xi power n pi. Now, this is nth moment, but we can compute, we can define what is called nth central moment. In x there is some bias, this is the bias, it is actually, it has some mean value may not be 0. the average value may not be 0. So, we actually bring that average value to 0 by subtracting the mean value and then take the moment, that is called the central moment. So, it is defined as x minus mx. We subtract mx from x, then this becomes a new random variable which has mean mx, and then this power n, you take the expectation. So, this will be x minus mx power n px dx, or if it is a discrete random variable, you take xi minus mx power n pi, summation instead of integration. Okay. Variance is denoted by sigma x square. It is defined as x expectation of x minus mx square. It is the second central moment. Second central moment is called the variance, and one can do or one can show after some manipulation that this is same as expectation of x square, the central moment, the second moment minus the square of the first moment. Now, if you have two random variables x1 and x2, then the joint moments can be defined as x1 power k, x2 power n, the product, the expectation of the product. Now, this expectation will be taken obviously with respect to the joint distribution of the two random variables. The either if they are continuous, the joint density function, or if they are discrete, take the joint probability distribution, probability mass function. Okay. So, this is the k nth joint moment. Previously, we had one random variable, we had one index, we called it nth moment. Now, we have two because there are two random variables, and we call it k nth joint moment. Okay. Now, similarly, we can compute the central moments. We can subtract the mean values and then get the central moments. And covariance is of special importance of x1 and x2. It is defined as expectation of x1 minus m x1 times x2 minus m x2, and one can show that this will also be same as expectation of x1 x2 minus m x1 m x2. So, this is the covariance of x1 and x2, these two random variables. And if we now have, instead of two random variables, say n number of random variables, so x1, x2, xn, n number of random variables, then we can define n square number of covariance between any pair of these random variables. So, for any I and j in this range 1 to n, you choose any two random variables, they may be same also, we can compute the covariance between those two random variables. If the random variable is same, you choose the same random variable two times, you will get this as the variance of that random variable. So, xi minus m xi times xj minus m xj, and then we can take the matrix with these components and that is called the covariance matrix. So, we can take this matrix mu 1 1, mu 1 2, mu 1 n, mu 2 1, mu 2 2, mu 2 n, and so on till mu n 1, mu n 2, mu n n. Then this is the covariance matrix. Basically, all the covariances are written as components of a matrix, and that this matrix is very useful. And one can also write this matrix as in a vector notation very nicely as expectation of the vector x. So, this is the vector, this is the x vector, and then this mean vector is the basically a vector with mx1, mx2 and mxn, that is the mean vector. Take the transpose, that is a, now you get a column vector instead of row vector, you make it column, then you multiply that by this same thing, but this is column, this is row. So, you get a matrix after multiplication. Then every component of the matrix is a product of this type, and then you take the expectation of all the components, you get this matrix. So, this is the covariance matrix. Now, one particular type of random vector is very important in this course, and we will just write that down. So, that is jointly Gaussian random vector. So, this is a set of vectors, set of random variables. So, x is x1 to xn, n number of random variables, and this is called a Gaussian random vector. This is Gaussian with mean. So, since this is a vector of random variables, the mean will also be a vector, mean of x1, mean of x2 and so on till mean of xn. So, that together they will form a vector. So, mean m and this is a vector, and the covariance matrix m. So, this is a Gaussian with mean m and covariance matrix m if the density function, if the joint density function is given by p x at the vector x is 1 by 2 pi power n by 2 determinant m power half. So, this is the covariance matrix, and e power exponential of minus half x minus m transpose matrix M inverse and then x minus m. One can check that the single random variable that we defined comes as a special case of this. So, if we take one random variable in this, that is n equal to 1, what happens? This mean vector becomes the mean of the random variable, this covariance matrix becomes the covariance, that is the variance of the random variable sigma square. Then what is the determinant of that matrix? Determinant of the scalar sigma square, it is sigma square itself. Then when you take power half, you get sigma here, and n equal to 1. So, root over 2 pi times sigma, then what do we get here? Here it matches with the density function that we considered before. And so, we had the Gaussian Gaussian single variable, Gaussian random variable density function was 1 by root over 2 pi sigma e to the power minus x minus mu whole square by 2 sigma square. So, mu is our m now, it is a single component. So, here it matched. Now, here half x minus mu transpose is same as itself, because it is a single component vector, it is a scalar, and m inverse is nothing but sigma square inverse, 1 by sigma square, and half comes here minus here and this square, this and this together gives you square. So, it matches with this for a single random variable. So, this is a special case of this. Okay. Now, we define what is called a stochastic process. So, far we are discussing random variables. Now, random variable is a single random quantity, whereas in practice in nature many signals that we get are random. So, many random functions are obtained, or random functions or random signals are obtained in nature. So, they are not, they do not fall in this category, because they are not simple one value, but the function has many values at different time. So, for example, the noise generated at the register, as I said before, that if you do not now consider only one time instance, the voltage measured at one time instance, the voltage might be changing with time. So, it is a function of time actually. So, that is a random signal. So, that is such a random quantity, a random function is called a random process. So, another example may be the output of a source generating a signal, random signal. For example, if there is a microphone, at the output of the microphone there is some voltage generated depending on the content of the speech. So, that voltage is a random signal, and those are modeled as random processes. So, those are called random processes. And the time in the random process may be discrete or continuous. Like it may be continuous, it is most of the times the the natural phenomenon that we observe, they generate continuous time signals. So, continuous time random process, but we can also sample them, then it becomes another random process with discrete time. So, that random process may be discrete time or continuous time. So, we have random processes continuous time or discrete time. And if we measure the function for a particular register, if we see what function we get, how the voltage is changing, and if we plot it, then we get one realization of the random process. It does not tell you all that is there about the random process. We are only seeing one particular instance of the one particular realization of the random process or stochastic process. It is also called stochastic process. So, or such a function is also called a sample function. It is like a particular outcome of an experiment. We are not observing all the outcomes, we are observing one particular outcome. Such a in this case of random process, we call that a single a sample function, because the observation is a function. Okay. So, now if we now take the value of a random process at a particular time, at a fixed time t1, so the random process will be denoted by xt or x n if it is a discrete time random process. So, if we now for the rest of the class we will consider mostly continuous time random process. So, this notation will not be used. And now, if we fix the time t to be t equal to t1, let us say, then we will denote that by x t1 or sometimes by x subscript t1. This will mean same thing as this. Okay. So, now if we take this, this is also a random variable, because the functions are random. So, the value at t equal to t1 is also random. So, at any time the value is random. So, it is a random variable, it is a real value, it takes real value. So, if you take any time, the random process value of the random process at that time is a random variable. Value of the random process at any other time is another random variable. So, if you take n number of times, you get n number of random variables. Okay. So, x t1 for any t1 is a random process, a random variable. And now, if you take some times t1, t2, tn, n number of times in decreasing order, then we can take x t1, x t2, x tn. They are random variables. And how do we characterize such n number of random variables? Obviously, by their joint PDF. If we are considering a continuous time random process, continuous valued random process, the value is continuous, then we have a probability density function, or which is abbreviated as PDF. So, we have a joint PDF, which is denoted by P, x t1 to x tn. Okay. So, now if we, so this density function, if it does not change, if we shift all the time instances by the same amount. So, if we have, if we choose a, so this is time, if we choose this and this time t1, t2, t3. Now, if I shift all the time instances by say 1 second, shift to here, shift to here, shift to here, you take t1 prime, t2 prime, that is t1 plus say tau, t2 plus tau and t3 plus tau. Then the density function of these random variables together, these 3 random variables, is same as the density function of these 3 random variables. If that happens, then we call that, we say that the random process is stationary. That means the behavior of the random process does not change with time. The statistical properties of the random process does not change with time. You take the joint distribution of some random variables picked at different times. If you shift all the time instances by the same amount, then the density function does not change. The joint density function does not change. So, in mathematical notation, it means that P, so x t is called stationary if, so x t is called stationary if P x t1, x t2, x tn. Actually, we should write x t1, capital X t1, capital X tn here, because this is the density function of, joint density function of those random variables evaluated at these values. But for to avoid cumbersome notations, we are not writing them here. So, this should be, if this is same as P x t1 plus tau, x t2 plus tau, x tn plus tau. If these two are the same density functions for any number of points n, any times chosen, that is t1, t2 to tn, and any shift chosen, any shift tau. So, then this random process is called stationary, and this is called strict stationarity. In fact, this is called strictly stationary if this condition is satisfied. there is a weaker definition that we will come across later, that is called wide sense stationary process. Often that is a sufficient condition in many applications. We do not need stationary process, but we need wide sense stationary process most of the times. Okay, so we have defined what is a stationary process. Now, correlation between two random variables xt1 and xt2, the correlation between these two random variables is defined, called as phi t1, t1, t2, and this is nothing but expectation of xt1, xt2 is the definition. Now, this is obviously, if you write it in terms of integration, it is nothing but minus infinity to infinity, minus infinity to infinity, x t1 x t2 p x t1 x t2 dt1 dt2, expectation of the product, and this is a function of t1 and t2. Now, you have chosen two random variables at two different times, but if you change the two times, the correlation changes. So, this correlation changes. So, this is a function of two variables t1 and t2, and this is called the autocorrelation function, because we have taken the same random process and taking two different time instances and computing the correlation between the random variables at those two different time instances. So, this is called the autocorrelation function of the random process that we are considering. So, this is called autocorrelation function. Now, if the random process xt is stationary, then this will depend only on, this will not change if I shift both the times by same quantity. So, if the process is stationary, then what will happen is, if the process is stationary, then phi t1 t2 will be same as phi t1 plus tau t2 plus tau for any tau. So, one can check that very easily from the definition, because this is invariant on the shift of the times. So, this is actually a function of how much gap is there between t1 and t2. Because if the gap is same, if you take any two other time instances so that the gap is same, then we can say that these two time instances is the shift of these two time instances. So, it is this is a function of the gap between the times t1 and t2. So, this is a function of t1 minus t2. So, it is denoted by phi t1 minus t2. So, we can call it a single variable. It is a function of only the gap, and if that gap is called tau, then it is nothing but phi tau. So, it is a function of the gap between the random variables. And so, for stationary process, the autocorrelation function is a function of only the gap between the time instances. Now, this condition may be satisfied even by a process which is not stationary. So, that kind of process is called wide sense stationary. So, if this is true for xt, Even if it is not stationary, but it is true for xt, then xt is called wide sense stationary. So, this is a wide sense stationary process. Now, we have been discussing from the beginning only the real random variable, that is the mapping is into the real numbers, set of real numbers, but we can also consider complex valued random variables, and it is everything is same except for some minor changes in the definitions, like the definition of covariance and correlation. So, there whenever there are two random variables coming in the expectation, one will be the conjugate, that is all the difference. So, for a complex valued random process, xt, then xt has a real part and imaginary part. Xt is say at plus bt, I bt. So, then the autocorrelation function will be defined as, the correlation itself will be defined as expectation of xt1 times not xt2, but xt2 conjugate. So, this half is not really very important. There are two parts, real and imaginary. So, this is scaled by half. Okay. So, for a random process, if there are now two random processes xt and yt, then we say that those two random processes are, these are random processes, then we say that they are statistically independent. These are independent if we take the random variable x at say x at t1, t2 till tn, and y at t1 prime, t2 prime till tm prime, and we take the corresponding random variables joint PDF, then that will factor as the product of these two separately, xt1 to xtn times py yt1 prime to ytm prime, and it is called uncorrelated if expectation of xt1 yt2 is expectation of xt1 times expectation of yt2. These are all usual definitions. For this is for all t1 and t2. Now, if we take the Fourier transform of the autocorrelation function for a stationary wide sense stationary process, then that is called the power density spectrum. So, if we have for a stationary process, we have the autocorrelation function, which is a function of the gap between the times. You can take the Fourier transform and let us call it phi of f. This is defined to be minus infinity to infinity phi tau, it will be a minus j 2 pi f tau d tau. This is called the power density spectrum of xt. This is a very important function. This is the Fourier transform of the autocorrelation function, and we can compute the inverse Fourier transform and get back autocorrelation function from the power density spectrum as phi tau equal to minus infinity to infinity phi f e to the power j 2 pi f tau df, the inverse Fourier transform. Now, from here we can see that phi 0, if you compute the autocorrelation function at 0, that is nothing but integral minus infinity to infinity phi f df. This is the area under the curved power spectrum, that function, area under the power spectral density function. But what is this? This is also, by definition, this is nothing but expectation of mod xt square. If it is real, then mod is not necessary. If it is complex, then xt conjugate. So, it will give you mod xt square. And this is nothing but the energy of the signal at t, average energy, average power in xt. So, this is always of course greater than or equal to 0, and so this is average power in xt. And what is this? This is the area under the curve phi f. So, area under this power spectral density function is the average power in xt. So, this actually gives you, this function gives you how much power is there in what frequency, how much average power of xt is there in what frequency. That is why this is the power spectral density. So, this is the power spectral density, power density spectrum. Now, we can take some, we can see some special cases. Common special cases are when xt is real, and that means, that will mean that phi tau, one can check that phi tau is real and even function. So, that phi f, the power density spectrum, will also be real and even. And then the next special case is when xt is complex, then what will happen is phi tau will be phi conjugate minus tau. It is because of the way phi tau is defined. Phi tau is defined to be expectation of x t plus tau conjugate. So, if we take x t plus tau x t conjugate, then that the whole product is the conjugate of the previous thing. So, as a result, at minus tau, phi minus tau will be phi tau conjugate, or phi tau is phi minus tau conjugate. So, this will imply phi star f is same as phi f. That means the conjugate is same as itself. This, so, what does it mean? Phi f is real. Okay. So, we have discussed about power density spectrum, and one very important type of noise that we come across is what is called white noise, where the power spectral density is a flat function. So, so example, white noise, where there is a flat power spectral density. In the two side, if you draw it in two side, then the density is usually denoted by n naught by 2, where n naught is the one sided density function, because if you add the density at minus frequency and plus frequency, you get n naught. So, this is n naught by 2 two sided density function, the amplitude is n naught by 2. So, what is the autocorrelation function of the white noise then? It is a delta function. It is the inverse Fourier transform of this. So, it is a delta function. That means that the autocorrelation at non-zero gaps is 0. So, that means if you take two time instances and consider the random variables of a white noise at those two time instances, then the correlation between them is 0. So, there is no correlation between the value of the noise at two different time instances. So, uncorrelated noise. So, white noise is basically uncorrelated in time. Okay. Now, it is also in this context, it is also very important to see what happens when we pass a stationary process through a linear time invariant filter. So, if you have a filter with impulse response h tau, and if we pass an xt, a random process through it, say we have a microphone and a voltage is generated and we pass it through the through a system, through a filter with impulse response h tau, what will be the spectrum, power spectral density of the output process? So, yt is minus infinity to infinity h tau xt minus tau. This is the convolution of input and output, input and the filter impulse response. And to compute the power spectral density of the output process, we need to first find out what is the autocorrelation function of this process. So, this is also stationary because this is stationary. So, phi yy tau is half, we consider in general a complex process. For real also it will be similar derivation, expectation of y t plus tau y t conjugate, this is the product. So, once we write this expectation in terms of their this can be written as this integration, each one can be written in terms of this integration, and then we get a expectation of double integration h tau 1 x t plus tau minus tau 1, you can call it alpha and beta, you can change the variables later, and then for this we can take h conjugate tau 2 x t minus tau 2 conjugate, then d tau 1 d tau 2. So, we can take this and we can find out what is the Fourier transform. We have to take another integral and find out the Fourier transform, and with some manipulation one can show that this will be, with some manipulation one can show that this will be the power spectral, sorry, not this, but the Fourier transform of this, that is phi y y f. This will be the power spectral density of the input process times h f mod square. So, h f is the frequency response of this system, that is, this is the impulse, h f is the impulses, is the Fourier transform of h tau. Then this is the basically power response, and this autocorrelation, this power spectral density will be multiplied by this frequency response to get the output power density spectrum. So, this is quite satisfactory because we know that if we transmit, if we pass a deterministic signal also through such a filter, the Fourier transform of this is multiplied by the Fourier transform of this to get the Fourier transform of the output. The output Fourier transform becomes the product of the Fourier transform of the impulse response and the input. So, here of a random process also similar thing happen, only this is now you have to consider the power spectral density. Power spectral density of the output is the power spectral density of the input times the power frequency response of the filter. So, in this class we have first considered some what happens to the how we can get the density function, probability density function of a function of a random variable from the density function of the original random variable. We have also considered functions of random vector and seen how to express the probability density function of the new vector in terms of the original vector's density function. Then we have defined random process and we have defined correlation function of a random process. We have defined what is a stationary random process, then wide sense stationary random process, and we have defined autocorrelation function, and the Fourier transform of the autocorrelation function is called the power spectral density or power density spectrum. And we have seen a particular example of a power density spectrum. There is a simple example, but it is a very important example because we will come across this in this course very often. There is the white noise. The white noise is a particular process for which the autocorrelation function is a delta function. That is, the power density spectrum is flat. And we have then discussed what happens to the power density spectrum of a random process if we pass it through a linear time invariant filter. The output of the filter will also be a random process, but that will have the power density spectrum which is the product of the input process power density spectrum and the frequency response of the filter. So, for example, if we pass white noise through a low pass filter, white noise has this flat power spectral density, power density spectrum. So, when we pass it through a low pass filter, the output will have a low pass power density spectrum. So, there is that kind of results will follow from what we discussed just now. Thank you.